Hello and welcome back. We continue our journey into neural networks and deep learning and now look at graph neural networks that are a very different way of building neural networks. Before we dive in, we need to understand what graphs are. So graphs comprise of the elements that are nodes or vertices and edges. The nodes represent entities, for example variables, and the edges encode the relationship between these nodes. We can have undirected edges or directed edges where the information flows along the direction of the arrow. Now let's take a more concrete example, a subway map. Here our nodes would be the stations, and of course each station has certain characteristics or features. For example, we may want to record which subway lane stops there, or the accessibility, or how many people can use the station at a given time, and so on. And then these stations are connected with the subway lines. So these are the edges. In the simplest case, we just have connections. Our graph is then a combination of the stations, the nodes, and the lines, the edges, and that makes up our subway system. We can of course make this a little bit more complex. We keep the stations as the node with their features, the node features, but now we add characteristics or features to the edges. For example, the speed of the trains that go there, or the operator that operates those coaches, or the number of trains that can pass through at a given time, and so on. Now again, our subway map or the graph is a combination of nodes and edges and builds our subway system, but both the nodes and the edges now have features associated with them. So what are graphs? Graphs are then again the combination of nodes and edges, but we can have features on different levels, and this is quite different to our machine learning and deep learning networks that we have encountered so far. We have the global attributes, for example the number of nodes, the average length, or anything that is associated with the graph itself. Then we have the nodes, and each node also has features. There can be the number of attributes or the node identity, but also everything that is connected to the node, the properties of this entity that the node represents itself. And we have the edge features. For example, it might be a directed or undirected one, the edge strength, but there might also be other properties of these connections between the nodes. So what can we do with it? Let's take another very simple example, a social graph, the Zachary Karate Club network, which is a staple of graph networks. Here the node represents the members, the students, and the edges encode the interactions between these members. Let's keep it simple and just have no edge features at the moment, and just say if two students talk to each other, they are connected. And this karate club has two instructors, Mr. He and Mr. John A. Now, before these two instructors got along quite well, and now they had a fallout and a big fight. So, as with any group, some students prefer one coach and one student prefer the other trainer. And a simple task would be then to do what's called node classification. We want to predict which student will prefer which instructor in the future. We could also extend this a little bit by have edge features. For example, the edge feature could represent the strength of the relationship or the number of interactions the students might have amongst each other. One key thing to keep in mind is that the position of nodes is not unique in this graph. So we can have many shapes of the same graph, but what matters in this constellation is that the nodes are there, but not their absolute positions and the features of their nodes, and the edges, which encode which node is connected to which other nodes. There are several application ideas. For example, we can focus on molecules. Here the nodes are the atoms or groups of atoms, and the edges would be the chemical bonds. We can use graph neural networks in this application for drug discovery. So for example, does a substance X produce effect Y? Or for example, what is the taste or smell of vanillin or glucose? So these affect the whole molecule, the whole graph. We could also predict the toxicity or how well it reacts with other chemicals and so on. We could also find applications in the field of material science. Here the nodes are again the atoms and the edges are the electron bonds or the electron structure in the crystal. So here our graph would be comprised of the crystal setup of our material. And then we could, for example, use this to predict crystal properties like the plasticity and so on. So how would we do this? First of all, we need to be aware that we have multiple levels of predictions, and this is one of the key differences to all the networks we've encountered so far. We can have predictions on the level of the whole graph. For example, the plasticity of a crystal or the toxicity of a molecule or the smell of vanillin, for example. We can also make predictions on the properties of individual nodes. That was, for example, what we have encountered in the karate network example. But we can also make predictions on the edge level. For example, we might want to predict if there is a connection and or how strong it is. So how do we build graph neural networks? And there are two main approaches in recent works: graph to graph and the message passing networks. And to some extent, these two approaches can be transformed into each other. We focus here on the message passing networks. The key idea is that we learn from neighbors. So that means we take information from neighbors, so we sit on a node and then look at the nodes that we are related to. This relationship, remember, is part of the edges. So we take information from the neighbors, process or aggregate this information somehow and pass this on. So let's take this simple example here, the node 2. In this graph, this is the one with the filled red dot on the bottom left. That has two direct neighbors, so this is what it's affected most. It's affected most by node 0 and by node 1. And as we can see, these edges have different strengths. So we take for example, the node feature, because we are connected to node 0, we are affected by node 0. So each node will have some set of features. So we take this information aboard, apply some function to it, and include this in our result for the node on the bottom left, the one we are at the moment, our node 2. Now we do the same thing for node 1, and so we have included the information from the two neighboring nodes. Now we need some sort of message passing function. As we said, we need to apply some function to it. We have the node features, and the simplest way we could do is apply a weight, like do a linear regression out of it. A little bit better, and this is where the network and graph neural network comes in. We built a simple neural network. We have a learnable weight matrix and a transfer function. And as you can see from the formula for f down here, this is the same formula that we had for a standard neural networks. We apply some correction B as well, but apart from that, is that what we've always encountered for simple feed-forward networks as well. The main difference here is that we need to apply this setup now in different ways, but the basic concept stays the same. So how do we combine the transformed node messages? So we need to include information from all our direct neighbors. For example, for our node 2 here at the bottom left, we have node 0 and node 1. So we need to take the information on board with the learnable weights in the small neural networks. So for node 2 we have now a set of information that we need to combine. We have the information from node 0, f of x0, and we have the information of node 1, f of x1. So this set of information needs to be put together so we can apply it for our node 2. There are, of course, a number of possible choices. We could sum them up with another weight, we could take the mean, or we can just take the maximum. And this gives us some sort of aggregated messages M bar from all the neighbors. Now we need to combine all these aggregated messages in node features, and essentially this is another neural network. You can see that the formula looks quite complex, but it goes back to the principle of building neural network nodes. So sigma again is our transfer function, the nonlinearity. We have the original node features. We have transformation functions, for example, our neural networks that learn how to combine information. And we have the aggregated information from all the neighbors. So essentially what we do is we need to take the information from our neighbors into account, build a small function f around it, and then combine all these different information from different nodes into our new state that describes our current node. And a simple example is to do this with a neural network, and again we use learnable weights to represent our neural networks. Now that we have the building blocks of doing this, we need to build a neural network out of it. And just as we did with other deep learning approaches like feed-forward networks and convolutional networks, we take this main building block and stack layers on top of each other. And then, just as we did with convolutional neural networks, we put a small feed-forward network in the end, the prediction layer. Remember that in convolutional neural networks we had the input images, then the convolutional part that essentially builds us features, and then the classification head, for example, to classify if this is a cat or a dog. Here we do the same thing, but with graphs. We have the input graphs instead of the images. Then we have the graph neural network layers that are essentially the convolutional neural network layers in the different contexts of convolutional neural networks. And now we have the prediction layer, for example, the classification head. But now, instead of cats or dogs, we first need to determine what we actually want to predict and on which level. Do we want to predict on the graph level, on the node level, on the edge level, or on several levels? And we made this connection to the convolutional neural network, and this is not an accident, because the message passing graph neural network infrastructure is somewhat related to spatial convolution on graphs. Remember that when we discussed the graph part, we said that we need to take the information aboard from neighboring nodes. And this is essentially what we do in convolutions for images as well. We take, via learnable filters in case of convolutional neural networks, we take the information of the environment or the surrounding of a given pixel into account and encode this. So on an abstract level, the message passing graph neural network approach is somewhat similar to the idea of convolutional neural networks.